All right, good morning, everyone. First, I'd like to thank the organizers for asking me to give this talk. I'm really excited to share some processes giving rise to Jupiter's satellite footprint aurora and some really recent results. This topic has been reinvigorated by recent Juno measurements across a number of instruments, and it's an active and really exciting topic, in my opinion. So this is, of course, a figure that has been shown numerous times with just a little bit of a different focus. Instead of looking at the main aurora, you can notice that there are footprints for the Galilean satellites, and they generate bright auroral spots, one of the most persistent features in Jupiter's aurora. It's been detected both across ultraviolet and infrared. And it is interesting fundamentally because it's a process that deserves more understanding. But it's also a very interesting example of a discrete situation in which we can understand the formation mechanisms and the sources for an auroral process. This is a figure, a really nice summary figure from Delamere and Bagenal, showing that a variety of physical processes in the magnetosphere map into the auroral regions into a bunch of different auroral signatures, but it's still very difficult to understand the origins and source regions of these, of where the physics is being generated for these auroral processes, with the exception of the footprint tails. We know exactly where the moons are, and so we can better constrain and understand these processes. It also allows us to better understand moon magnetosphere interactions as a whole. So there's a variety of big open questions related to the footprint tail aurora. For example, what are the microphysical processes sustaining these interactions? How and why do they differ between the Galilean satellites? And then how do these relate to a broader magnetospheric and auroral phenomena and extend our understanding of auroral processes? For the next part of the talk, I just want to start from the local interaction all the way up until how we generate the emissions, just from a stepwise setup, and then transition to the morphology and the complex details of these footprints, and then finally share some recent and discoveries from the Juno mission that have been challenging our understanding of these auroral processes. So first, Io is probably the best understood, and so the majority of this will be focused on Io, but all of these should extend to at least the 3 inner Galilean satellites. So at Io, you have a co-rotational flow moving past Io at about 57 kilometers per sec. There's a number of phenomena that occur. You have charge exchange, you have pickup ions and mass loading, a slowing down and diverting of the co-rotational plasma. And all of this serves to then set up an electric field away from Jupiter and a current system, again, that starts from the Jupiter side and goes away, and then closes eventually in Jupiter's ionosphere. The power of this interaction varies as Io moves throughout its orbit because it bounces up and down in the centrifugal equator. And so, for example, it sees in this middle panel density variations that are symmetric between its 2 peaks. However, when it is in the center of the centrifugal equator on both different sets of longitudes, it encounters a different magnetic field strength. And the power that's generated at Io is a function of the speed, the size of the body. This is something like the size of Io, the magnetic field strength, and the density of the plasma. And all of this means that there's an expected asymmetric, one of the times that it goes through the centrifugal equator is a stronger expected interaction than the other. So then this current system launches Alphane waves at about the scale size of Io. They go both north or of any moon, they go north and south. And they're bent back in an Alphane wing with an angle that's dictated by the local plasma flow speed and then the Alphane speed. And that dictates what bend back you get. The local Alphane speed at Io, for example, is a few hundred kilometers per sec, as shown here by Lysak and colleagues, and then it can go up to the speed of light near Io, and so there's some interesting phenomena we'll cover in a little bit on what arises because of that. So then, as I mentioned, for at least the 3 inner Galilean satellites, we anticipate that there's this consistent set of Alphane wings that have been launched from all of them. And they all connect, again, back to the auroral features and can generate these interesting aurora at Jupiter. I'll also mention that at Io and Europa, the scale size of the interaction is roughly the moon, but the barrier at Ganymede is a bit more inflated because of its intrinsic magnetic field. So then these Alfvén waves, they propagate up towards the ionosphere, and they can couple with the electrons and ions, as we'll talk in a little bit. As Bob mentioned in his talk, you can get parallel electric fields. They're peaking somewhere in this shaded region here. They can oscillate. They can go bidirectionally, so you might expect bidirectional broadband electron acceleration from this. I'm not going to go through everyone. I just wanted to list a bunch of references, and this is not even inclusive, but there's a lot of ongoing activity in studying these wave particle interactions. You can also get Whistler mode emissions from the field-aligned beams, and then from the upward loss cone, you can get radio emissions. So there's some posters on this afternoon that are further discussing this. We were very fortunate to actually fly right through Io's main Alfvén wing and observed a variety of diverse and fascinating plasma physical processes. On the left here is shown the electron measurements from the JADE plasma instrument. The top panel shows upward electrons. The bottom this third one shows downward differential energy flux. The middle panel is the pitch angle distribution, and what you can see is there are full upward and downward loss cones. The particles in this population are being actively accelerated down into the planet and generating aurora. This population is getting accelerated the other way in this oscillating bidirectional parallel electric field. It also means we probably flew right through the acceleration region. We saw peak electron fluxes, energy fluxes of hundreds of milliwatts per meter squared, which is more than adequate to generate the auroral emissions and the brightness. And the electron distributions were power law-like, very consistent with broadband. Additionally, and one of the interesting surprises is we saw proton acceleration, transverse proton acceleration. This second panel shows the pitch angle distributions for energetic particles coming from, measured by JEDI. This is from a paper that George Clark is leading. They're peaked kind of off the loss cone. And this is due to being transversely heated and then moving up the magnetic field line from the magnetic mirror force. And in a really nice paper by Ali and many colleagues, they found that the energy coupling, they looked at the waves that we saw during that time. We had a variety of wave modes observed. There was alphanic. You can see this vertical stem here, this dispersionless alphanic feature. There was this dispersional ion cyclotron feature that stops at the ion cyclotron frequency, and then there was Whistler mode emissions. And these ion cyclotron waves, analyzing how much power they could transmit to the ions, were consistent with the conics that we measured. All of this is in this very interesting picture that the wave particle coupling is very diverse and across many different species of charged particles. So the electrons that go crashing into the atmosphere then generate these bright aurora, and they also have time modulations. This is from a showing Ganymede, for example, will transit inside and out of the plasma sheet, and there are large variations in the auroral brightness, in part due to this phenomena, this sinusoidal phenomenon. So that was just the physics of the main spot, but then those Alfvén waves that are launched from Io will then continue to bounce. And this is a figure from Gurnett and Gertz, 1981, showing that these Alfvén waves may continue to bounce all along the orbit. The extent to which those Alfvén waves may interact with each other can be parameterized in terms of the strength of the interaction. This is from a figure from Joachim's paper. And as shown in some more recent studies, both the conductivity in the ionosphere and the strength of the interaction can all govern how these multiple reflections will transmit power to the electrons and how they would manifest in auroral emissions. And they're a signature for a number of different features at Jupiter. Those reflections have been proposed to be one of the two explanations for why we have a auroral footprint tail. So it was always agreed upon what generates the main spot, but there were two physical processes that were proposed, both completely valid, that it was unclear on which one nature had picked until we really got there with Juno. The first process was that instead of the tail being also generated by Alfvén waves, that there was a slowdown in the plasma behind the moon. And to pick that back up, you need a steady state current system, which then generates these quasi-static electric fields and accelerates electrons into the atmosphere. The other proposal was that these Alfvén waves keep bouncing and keep accelerating in a very similar phenomena as what's generating the main spot. Before we got there with Juno, there was observational evidence that preferred the latter, the Alfvénic acceleration. This is from a paper Bertrand led, where he looked at the vertical extent of the Hubble Space Telescope emissions from this. And here's what's shown as the brightness distribution as a function of altitude. And then looked at what a variety of different incident electron distributions might manifest in an altitude profile. If we were quasi-static acceleration, you might expect a Maxwellian or minor energetic, and those were not consistent with the altitude distribution. What was essentially spot-on match was a kappa distribution here compared to the observations that were then very consistent with broadband acceleration from Alfvénic electron acceleration. Then when we got to Jupiter, that largely confirmed this interpretation with a little bit of extra spice, I would say. So Ios, this is the electron distribution now for Io as a function of energy. And we found that it was largely broadband all the way out throughout the tail. These are just kind of an average of tail measurements. Ganymede had some similar properties as well. And Europa was a bit of an oddball. It was kind of neither. It wasn't very peaked and it wasn't exactly monotonic. And this is still an open question. And I'd encourage everyone to go see the poster by Jonas this afternoon, where he's also looking into the comparing and contrasting these different moon interactions. I'd also mention that Alfvénic acceleration has been supported by recent simulations as well. The morphology specifically of the moons, you have a main spot and then sometimes a leading and a trailing spot, and they also differ in altitude. And this was proposed as another paper from Bertrand that suggests that this is all, again, part of a Alfvénic reflection setup. Here's an example where Io is in the northern part of the torus. You get a little bit of bend back, and then that Alfvén wave escapes at the speed of light and generates a main spot. Electrons get accelerated both ways, and so the ones that go south form a conjugate aurora and a leading spot here. And then in the south, there's a bend back that causes a lag, and so you get the main spot that's offset from that leading transhemispheric electron beam. And then you get continual bounces of these and TEBs, and it sets up this complex tail structure. So here's it's dynamic in time. You can see that these main spots and reflected spots bounce and interchange. And same with the TEBs, the transhemispheric electron beams that are accelerated from the opposite hemisphere. They also kind of switch back and forth with that main spot. This interpretation is well supported by the data. For example, for the case we were just looking at, you have a leading spot as a function of longitude here. And then in the south, the main spot, in the south, you get a leading spot that were electrons from this going the other way, and an offset main spot. And then as Io goes the other direction, you have a main spot, and on the northern hemisphere, you have a leading spot from electrons coming up that way. And so this is largely supported by the data remotely. But what's been really exciting is that with Juno, we've been able to challenge and confirm or contrast some of these theories. This is a very recent paper by Vincent Hugh. And just like we got lucky to fly through Io's main Alfvén wing, we flew through Ganymede's transhemispheric electron beam. And so here you can see Ganymede's main spot and transhemispheric electron beam coming from the opposite hemisphere. Here we were in the south, so these are electrons coming from the north. And I'll just focus your attention up here. This is the downward energy, the downward electron flux as a function of time. And here you can see there's a lot of downward electrons in the higher energies above a few keV and kind of a depletion in the lower energy component. This is exactly what we would expect if electrons came from the other hemisphere. The low energy electrons interact with the material in the plasma sheet. and they don't make it to the other side, and we would very much expect a distribution like this. So this confirms this transhemispheric electron beam proposition very well. And again, like Fran said, I'd encourage you to see Vincent Dahl's poster. We've also been able to understand statistically now. We cross these trails twice at least every orbit. Sometimes we see things, sometimes we don't. But this is on the left here. This is a figure that shows a variety of quantities as a function now of how far down tail we are. Something we learned in analyzing this statistically is that the best organization for the IO footprint tail data was as a function of an angle where you trace alphane waves back from the position of the aurora to Io's orbit. And so, for example, this angle is from Io along its orbit of two different alphane waves launched to the ionosphere. And organized as a function of that angle, we found that the electron energy flux, for example, decreases with an e-folding distance of something like 20 degrees. And we have coincident measurements of the Poynting flux, the energy available for alphanic acceleration. And that's what's shown here in yellow. And you can see that also decreases monotonically approximately. And there, fortunately, in terms of a physical explanation, it's always higher. This is the available energy to then create that. This second plot shows kind of the inverse of the length of that line, the efficiency. The farther they are away, the less efficient the process is. And here, got efficiencies of something like 6 to 12% coupling from the alphanic available energy to electrons, which is consistent with a filamented interaction. There was also some trends that sometimes, even though we were in closer, we would get lower emissions. And that might be explained because it has to do with where Io was when it launched these alphane waves. If it's in the core, in a stronger interaction of the torus, or if it's in the north or the south, it has different strengths of interaction. And finally, we've been able to characterize very well now as a function of all longitudes the emissions, and I'd encourage you to see Vincent Hughes' paper or poster today as well on that. Just a few more highlights. So one of the interesting and cool surprises was that there was a variety of proton acceleration. So electron was always expected because we know that that's what generates the aurora. But what you can't see is, and invisible to us in a sense, is all the other acceleration not generating the aurora. We found that both in the low energy, this is J, this is a few keV here, and in the very high energy, up to hundreds of keV, there was a bunch of different proton acceleration. Like I mentioned, there's perpendicular proton acceleration from ion cyclotron waves, and that's probably occurring somewhere around in this distance or lower. We also found that there might be evidence for acceleration at the torus boundary, and I think this is still an open issue on how you can get coupling between the alphane waves or whatever type of wave mode to the ions. I'll also mention the infrared measurements have just been wonderful in understanding the substructure of this. This is a figure from Alessandro's paper in 2018, showing just an incredibly diverse and turbulent tail, and it's an active area of research. This is from a paper, and I won't say too much because this talk will be very soon after this one, showing that this might be explained by multiple bounces, not just from ionosphere to ionosphere, but through the torus boundaries themselves without transiting it. And see the poster today, Alessandro's poster as well. There's also another talk, and that, again, I won't say too much about this, but there were some structures that were fixed with Jupiter and not with Io's position, and so there might be some ionospheric feedback in which there's enhancements and local modifications in the ionospheric properties, and so stay tuned for an explanation on that. And finally, and last but certainly not least, and there's a variety of other phenomena, we were surprised to see that the tail splits sometimes, not others, and we see it in the infrared observations because it has the resolution. We also see it in the low energy and the high energy particle data. And it's an open question on, is this due to the interaction of Io, or is it some evolution of the tail and these alphane bounces? So with that, I will just end by saying there's been a ton of recent publications that have been led out of the Juno data set, and it is ripe for the picking. There's a ton more work to be done, but I'll just mention that all the way from the energetic electron dropouts and processes kind of in the near moon, all the way to acceleration, alphanic fluctuations, electron acceleration, proton acceleration, conics, radio emissions, and then substructure of the tail, split tail, emissions variation. There's just a ton of phenomena that we've been able to understand more, and it's a really exciting time. And so thank you.